Ionic compounds lesson. In this lesson, we're going to be talking about ions, ionic compounds, drawing ionic compounds, some examples, naming ionic compounds, ionic compound formulas, the criss-cross rule, multivalent compounds, and then properties of ionic compounds. Ions. So metals, typically on the left-hand side of the periodic table, lose their electrons and become positive. They become positive because they are less negative, keeping in mind that electrons themselves are negative. So if you lose an electron, electrons, then you are less negative. Less negative equals more positive. So all our elements that lose an electron, like sodium, become positive, and that's how we're drawing here. So when sodium in this top drawing loses an electron, then it becomes this positive ion that we see below. Nonmetals, typically on the right-hand side of the periodic table, gain electrons and become negative. It's just like we talked about before. So if you are getting electrons, so if you gain a negative electron, you become more negative. Now, what's the total charge if you have a positive, like our sodium here, and our negative, like our chlorine here on the right? Well, if you get +1 plus -1, you get 0. You get a neutral compound. And that's going to be the basis behind our ionic compounds. When you combine two ions, you get a neutral ionic compound. Ionic compounds. Metal and nonmetals combine to form ionic compounds. And at this point, they're going to be neutral, because we're going to have, remember, the +1 plus -1 from the previous slide equals 0. This 0 means that it's neutral. The metal atoms lose electrons to form positive ions. The non-metals gain electrons to form negative ions, like we had before. The two join together to form ionic compound, which is electrically neutral, like we just pointed out at the top here. So if you have a neutral object, that's an object that has 0 charge. An example of that is sodium chloride, or table salt. Table salt has a neutral charge. It's 0, whereas the ions that make it up, the sodium plus and the Cl negative, were charged. So two charged particles come together to make a neutral compound. Ionic compounds. Ionic compounds are formed when a metal gives one or more of its electrons to a nonmetal. When all the electrons are gone, the metal's inner orbit of electrons is full, and this makes the metal stable. A good example of that is sodium. So we're going to zoom in here, and we're going to draw the Bohr-Rutherford diagram of sodium so we can see what we're talking about. So sodium has 11 protons and 12 neutrons in its nucleus. In its first orbit, it has 2 electrons, as we've talked about before. That leaves 9 electrons. So we'll go 1, 2, 3, 4, 5, 6, 7, 8. And then we have one more orbit, and we only have 1 left. It's this 1 electron up here that's going to be the thing that the sodium atom wants to get rid of in order to become stable. Now, the reason for that is that if it loses that electron, then this outer orbit actually disappears. And let's zoom in again and have a look at what that means. So I'm going to erase this outer electron. And as we do, the whole orbit disappears. Very similar to when you're looking at a planet orbiting the sun. If you were to remove that planet, the orbit that it goes around the sun in, it doesn't exist anymore. It's not a thing on its own. It's only a thing when that planet is in its place, when it's going along that orbit. It's the same thing with the electrons. If you remove the electron in the outer orbit, it goes away. So now what are we left with in the outer orbit of sodium? Well, we have 8 electrons, and that's what sodium wants. Sodium wants 8 electrons, so now that sodium is happy. Now, how do we draw the Lewis structure for this particular diagram? I'll do it down here, and it's just simply going to be sodium with a plus. The atom has lost electrons, so it takes a positive charge, and that's what we've drawn here in the top right-hand corner. So no brackets, no numbers. In this case, we just lost 1, so it says Na+. So another example of that is calcium. So calcium has 2 valence electrons, and when it loses those 2 valence electrons to become a calcium ion, we write it as Ca2+. Ionic compounds. The nonmetal receives 1 or more electrons to fill its outer shell and becomes stable. Outer shell, outer orbit, same thing. If we draw the Lewis structure for the nonmetal, we include the full valence orbit, brackets, and the charge. And that's what we see here at the bottom. So you can see that we got 2 electrons for oxygen. Oxygen originally had 6. We get 2 extra electrons, and now it has 8. It gained 2 electrons, so now we have a negative charge of -2. We have the brackets around, and we have full 8 electrons orbiting around oxygen. The resulting positive metal and negative nonmetal stick together by the electrostatic attraction. Opposites attract, so you have a positive calcium and a negative oxygen, and they're going to come together. So Ca2+ is going to be attracted to our nearby O2-. Since one is positive, one's negative, they attract to each other. And that's what we see here in this diagram. So putting the compound together, we can see that the overall molecule has a neutral charge. It has no charge because it was +2, and then it's +2, and that equals 0. This particular example is simple because the calcium and oxygen want to exchange the same number of electrons. But what do you think would happen if they want to exchange a different number of electrons? So what I want you to do is pause the video and draw the ionic compound for lithium and oxygen. So the first thing we're going to do is we're going to draw the Lewis structures for the atoms on their own. So lithium has 1 electron, and oxygen has 6 electrons. North, south, east, west, north, south. Now use an arrow to show the electron transferring from the lithium atom to the oxygen atom. So we're going to go like that. So you can now see that the oxygen atom still doesn't have a complete outer shell, right? It's still missing 1. It has 7, it doesn't have 8. So clearly we need another lithium to complete the process. So we're going to put another lithium down here, and we're going to show the transfer of this electron up to that spot right there. The lithium atoms, having lost 1 electron each have a charge of +1, and we can see that in here and in here. The oxygen atom, having gained 2 electrons, has a charge of -2, and we can see that here. The final Lewis structure is illustrated here. So we have the final Lewis structure there, and we have the molecular formula right there, Li2O. Now it's Li2 because we have 2 lithiums, 1, 2, and we have 1 oxygen, so just 1. So pause the video and try it for aluminum and oxygen. So first thing we need to do is draw the Lewis structure of the individual atoms. So once again, let's draw aluminum. Aluminum has 3 valence electrons. It's in the 3rd group on the periodic table, and oxygen once again has 6. North, south, east, west, north, south. Use the arrows to show the transfer of electrons. So one more time. Now aluminum has 1 electron left, so we need another oxygen atom. So let's draw that. North, south, east, west, north, south. We draw this guy going here. But now oxygen is missing 1. Right now this bottom oxygen only has 7, so we need to draw another aluminum. 1, 2, 3. And we're going to transfer this electron here. But now this aluminum has 2 extras. So we're going to draw 1 more oxygen, and then we should be good. North, south, east, west, north, south, and then we're going to go like this and like that. And now we're good. All our atoms that we're using here have a full outer orbit. The aluminums have lost their outer orbit, and the oxygens have gained enough electrons to fill their outer orbits. And so here's the Lewis structures for the ions involved. We have our 3 oxygens, 1, 2, 3. We have our 2 aluminums. They're both +3 because they both lost 3 electrons, and all our oxygens gained 2, so they're -2. Now the way that we try to draw our Lewis structure is we're going to try to space out the atoms as equally as possible so that the ones that are like charges aren't near each other. This is difficult to do all the time, but in essence what you're going to do is you're going to try to put the negatives around the outside and try to keep them away from each other. Name ionic compounds. So how do we name ionic compounds? Well, number 1, we write the name of the metal. Number 2, we write the name of the non-metal, changing the end of the non-metal name to IDE. So for example, sodium chloride, calcium oxide. So you have our metal first, we have our non-metal second, and we change the ending of the non-metal to IDE. Writing ionic compound formulas. The trick is to find the number of bonds each atom involved will make. The easiest way to do this is to refer to your periodic table. So the strategy we're going to use is we're going to number the groups 1 to 3 going from left to right while skipping the transition metals. Remember, the transition metals are all these guys here. Number the groups 1 to 3 going from the right to left. Again, we're going to skip a column, we're going to skip the noble gases. So these are the noble gases, we're going to skip them, and now we're going to go right to left. So remember, for the metals we went left to right, 1, 2, 3, and now for the non-metals we're going to skip the noble gases and go 1, 2, 3. These numbers represent a charge on the ion. It also tells us the number of bonds that it will make. So you can see we went from 1, 2, 3 to +1, 2, and 3. We went from 1, 2, 3 on the right to -1, 2, and 3. Then what you need to do is write out the atoms with their stable charge, as we just found by doing this. Then cross the numbers to the opposite atom and remove the sign. This is called the criss-cross rule. So for instance, if we have aluminum and oxygen, we wrote aluminum on the left with its 3+, because we know aluminum is found right here on the 3rd column right here. Oxygen we know is -2 because it's found in this group right here. So we write Al 3+, O -2, and then we cross them over, we remove the signs, and we're left with Al2O3. If possible, you want to reduce it to lowest terms. So for instance, Ca2O2 becomes CaO. The criss-cross rule, aluminum chloride. So number 1, we write out the name with a space. So we write aluminum chloride. Step 2, write the symbol with their valence number. Step 3, crisscross valence numbers as subscripts. And step 4, combine as a formula unit, AlCl3. Let's try magnesium oxide. So the first thing we're going to do is we're going to write the names. That's step 1. Step 2 is we're going to write the charge number up top. So magnesium has a charge of +2, so we write Mg2+, and oxygen has a charge of -2, so we write O -2. Step 3 is we're going to take the charge number, so in this case, +2, and we're going to move it as the subscript in oxygen. We're going to take the charge number for oxygen, which is 2, and we're going to make it the subscript of magnesium. We're then going to rewrite MgO2, and then we're going to reduce. They can both be divided by 2, right? This Mg2O2, the 2's can be divided by 2, and we get MgO, and we never write the 1's. Multivalent compounds. These will include the transition metals, as well as a few other ones. When atoms get larger, their atomic structure can become more complex. This means that some atoms can have different numbers of valence electrons in their different situations. For example, if we look at the Lewis structure of copper, it can have 1 valence electron, and it can have 2 valence electrons. Clearly, this atom can form more than one type of molecule. For instance, if it's going to bond with oxygen, it can have a situation where there's 2 coppers and 1 oxygen, and it can have a situation where there's 1 copper and 1 oxygen, depending on the valence number. If it's copper 2, like we have on the right-hand side, then we only need 1 copper. If it's copper 1, like we have on the left-hand side, then we need 2 coppers. So if you're not familiar with where the transition metals are, they are the ones in the middle here. So these are going to be our multivalent. Most of them are going to be multivalent, mind you, but there's also going to be a few other ones in the other spots, namely over here, that are also multivalent, that you're going to need to be told of ahead of time. Multivalent compounds. So we need to distinguish between 2 or 3 different ion forms. To distinguish, we use the Roman numerals from 1 to 7, which corresponds to +1 to +7. It's always plus. That's the key. These are metals. Metals are going to lose electrons, so it's always going to be plus. For example, nickel can have 2 ion forms, Ni2+ and Ni3+, and these are named nickel 2 and nickel 3 accordingly. Multivalent compounds. When naming these compounds, we need a method of distinguishing CuO and Cu2O. You need to put a Roman numeral to indicate the charge in brackets in between the metal and the non-metal. Remember, it's the original charge. The Roman numeral is only included if the metal is one of the atoms that can exist in more than one charge. It's only included if it's one of the multivalents. So try to write the name for the following compounds without looking at the next slide. So I want you to pause the video and answer these 3 questions. So for the first one here, we know our atoms are going to be copper and fluoride. Now we need to know what that bracket was, what that charge on copper initially was. So how do we do this? Well, we're going to need to go in reverse of the crisscross rule. Remember, crisscross rule, you had up top, bringing down to the bottom. Well, now in the reverse crisscross rule, you're going to take from the bottom and go up top. So fluorine with a 1 down here is going to go up there, and copper with a 1 down here is going to go up there. So since this 1 from fluorine went up top, we know that it was copper 1. PbI2. Pb is lead, bracket, iodide. So we're going to do the reverse crisscross. There's a 1 beside the Pb, so we bring it up there. That doesn't really matter at this point, but we're going to take this 2, and we're going to bring it up there. So we know that Pb had a charge of +2, so we're going to put 2 here. And our last one, calcium fluoride. I tricked you. Because of course, calcium is not a transition metal. It's not a multivalent. It is in group 2, so we do not need to write the brackets. So it's just calcium fluoride. How do we know which Roman numeral is going to be used? Well, we just went over this. So for number 1, CuF, we're going to do the reverse of the crisscross method, take the subscript and use it as a charge on the other symbol, and then put the metal charge in brackets. So Cu1F1, which is what CuF is, we bring the 1 from beside the copper and put it up by the F. We're going to take the 1 beside the F and put it up here by the copper, and we're going to get Cu +1, F -1. So we know that there was a charge of +1 on copper, so it becomes copper 1 fluoride. In the second one, PbI2, remember there's always a 1 if there's nothing listed. So we're going to write that 1 right here, and we're going to bring it up top above the iodine. We're then going to take the 2 beside the iodine and put it up here beside the Pb. So we know that Pb had a charge of +2. So we write it as lead 2 iodide. So some exceptions to keep in mind. Silver, Ag, is always a charge of +1. Zinc always has a charge of +2. Now I mention these because they are in the transition metal section, and they have a set charge. It's not multivalent. So also you need to be careful when asked to determine the Roman numerals given the formula. So for example, Cus. What you would normally do is write copper 1 sulfide, because you take the 1 from here and bring it up top, and the 1 from here and bring it up top, and you'd be left with copper 1 sulfide. However, you need to check that the charge on the anion is correct. This is super important. Sulfur has a charge of -2, so we need to keep that in mind. So in this case, it would be a -1. However, if we look at the periodic table, we know that sulfur is -2. Therefore, we need to multiply both charges by 2 to get it there, right? Because you brought the 1 up by the sulfur. So it was C, also write it over here again, Cus. The 1 was up here, as in it was -1, and this was like +1. We know sulfur is -2, so we multiply it by 2, multiply that side by 2, so we get copper 2 sulfide. Very important, and something that a lot of students get tripped up on, so make sure that you understand what's going on and how to check. Check your understanding. So pause the video and answer these two questions. Calcium nitride. So we're going to do calcium and nitrogen. We know the charge on calcium is +2 because it's in the second group on the periodic table. We know the charge on nitrogen is 3-, and then we're going to cross them over. And we're left with Ca3N2. Gold 3 oxide. Gold is one of those multivalents, and we know that because we have the brackets here, right, with the Roman numeral. So gold's symbol is Au, oxygen's is O. We know the charge on gold was 3+. We know that because it says it right in the question. We know the charge on oxygen is 2- because it's in that group on the periodic table. We're then going to cross them, and we're going to be left with Au2O3. Check your understanding. In this slide, we're going to be writing the name given the formula. So in this case, first we have Fe, which is iron. Now iron is a multivalent, so we're going to put brackets, and then we're going to write oxide. Now we need to do the reverse crisscross like we were talking about. There's a 1 down here by iron and a 1 down here by oxygen. So we're just going to blow it up here. We're going to move that 1 up here, and we're going to call that -1. We're going to take this 1 here, and we're going to move it up here, and we're going to say +1. So if this was the case, iron would have a charge of +1, but we need to double check. We know that oxygen has a charge of -2. To make -1 equal to -2, we need to multiply it by 2. What we do to oxygen, we need to do to iron, so times 2, and we're left with a charge of +2. So now when we go back to our question, we know that it must be iron 2 oxide. Au is gold, bracket because gold is a multivalent, and then S is going to be for sulfide. So we're going to zoom in again, and we're going to take this 3 on sulfur, and we're going to move it up here, and we're going to say +3. We're going to take the 2 from gold, and we're going to move it up here, and we're going to say -2. Then we're going to check our periodic table. Sulfur does have a charge of -2, so that's correct. So we know that one's correct. So now when we zoom back out again, we know that gold has a charge of 3. So 1, 2, 3, and we're done. Properties of ionic compounds. Many ionic compounds are soluble in water. When they dissolve, they separate into their individual ions. So water molecules do this by surrounding each ion and preventing it from rejoining. So if you take a look on the left here, that would be an example of a sodium chloride crystal. If you put that crystal into water, the water molecules that are all around surround all the individual ions. So you get a situation like this where the sodium can't go back to the chlorine because it's surrounded by water molecules, and the chlorine can't go back to the sodium because it's again surrounded by water molecules. So they're separated from each other, and they're kept separate from each other. Properties of ionic compounds. They are hard, brittle solids with high melting points. Many are also electrolytes, which means they conduct electricity when dissolved in water. As a matter of fact, pure water, which everyone thinks is a high conductor of electricity, is actually a very poor conductor of electricity. It's the dissolved ions that allow the water to conduct electricity, not the water molecules itself. And that concludes our lesson on ionic compounds.